Welcome to Hartman Math. Today we're going to look at solving systems of equations. A couple lessons that kind of blend together here, 7.1 and 7.2. We begin with the substitution method. So to take one of the equations and solve for one of the variables in that equation. And then to substitute that expression that you found into the other equation. And then we can solve for one of the variables. Once we have that and you solve and get x equals or y equals, we can back substitute into the other to solve for whatever variable or variables are remaining. And then if you would like to, and if it's important, and if you want to make sure you got it right, we should be able to check our solutions. So example number 1. Solved by substitution, we could solve either equation for x or for y. And I definitely think the second one might be easier. So if we were to solve for x, and if you decided, hey, I wanted to solve for y, there was really no harm in that. But if we solve for x by adding y to both sides, we get x is y plus 5. We're then going to substitute that into the other equation. So y plus 5 gets squared, that quantity squared, plus the 2y equals negative 2. So we'll need to square this quantity. So y plus 5 times y plus 5, multiply it all out. Do not distribute the exponent, that will not work. And since it's quadratic, we probably also want to get it equal to 0. And we're going to end up with y squared plus 12y plus 27 equals 0. We can now attempt to factor. If that didn't work, maybe complete the square, quadratic formula, different methods that we have of solving quadratics. But I think this one does factor. And so according to the zero product property, y equals negative 9, y equals negative 3. It's not the solution. Remember, we do have x's as well. So from the negative 9, plugging that in here, negative 9 plus 5, we get an x would be negative 4. So that is, we're going to write that as an ordered pair, x comma y. And then for the negative 3, plug that in, negative 3 plus 5 is 2, x is 2. So we get the point 2 comma negative 3. We can check that in both if you want to make sure that we got it right. So now we're going to try the same exact thing with a graphing calculator and see if we happen to get the same answers. So we want to go to the y equals screen. And if we take a look at our first equation, we're going to need to solve that for y. So perhaps we subtract the x squared on both sides and then divide by 2. So it might look something like parentheses, negative x squared. Also remember, if you get an error message, you might have put subtraction here instead of the negative. So negative x squared minus 2, close parentheses, divide by 2. That's solving the first equation for y. The second one, we have to solve that one for y as well, so I'm going to arrow down and solve for y. So y equals x minus 5. I'm going to do a quick window check. Let's start with the standard window, see if we need to adjust from there. We look good, so I'm ready to press graph. Pretty good. I think I'm going to adjust my window a little bit just so I can see this a little bit better. Maybe a little bit lower here, not so much up here. Just might help us navigate this a little bit. So I'm going to go back to my window. And as I said, I want to go on the y min, I want to go a little bit lower, so maybe negative 15. And the y max We didn't really have anything up there, so we'll just say 5, something like that. Just get a little bit better picture of this. All right, so now what we're looking for is where are our equations, our functions intersecting. That's where we're going to have solutions. So anytime we want to be exact, we need to calculate. So trace gets you close, but we want to calculate. So second trace. What is it that we want to find? We want to find where they intersect. So arrow down or just choose 5. So it's going to ask you, because you might have more than the 2 curves, it's going to ask you which one is your first curve. You have to choose which one. So yeah, that seems reasonable. That's our first one, the parabola. So I'm going to hit enter. And then it's going to ask you, is this your second curve? And if it's not, just arrow down. It'll jump down to the next one. But this is, so we're good. And then usually I don't have a guess. But what's going to happen here is we do have 2 points of intersection. So I want to get closer to one of them. If I want to find this one first, I'm going to help it along with a guess and just kind of arrow to the left. Just get close there, hit enter, and here we are, -4, -9. That should have been one of ours. Let's try this again. Second trace for calculate, intersect. A little bit hard to see it this time, so I'm going to kind of arrow to the right, jump up. Is that my first curve? Yes. Second curve? Yes. And now to guess, I got to go over to the right to get closer to that one so that it narrows down on that one. And we've got 2, -3 over on this one, and that's how we might solve it using the graphing calculator. Example number 2, a total of $25,000 is invested in 2 funds paying 7% and 4% simple interest. The yearly interest is $1,405. How much is invested at each rate? Probably a really important part to this is figuring out what variables we're going to use and what they're going to mean in the problem. What we're trying to find is how much was invested at each one. Those should be our variables, whatever letters that you choose to pick. But be specific. They need to be something measured or countable. So we're going to say let X be the amount invested at 7% and Y be the amount invested at 4%. So we should get a total investment equation. So think about what that might be. Amount plus amount equals total. So X plus Y equals 25,000. And then we've got an interest equation. The interest from this one, 0.07x, plus the interest from this one, 0.04y, equals total interest. And what I chose to do in that is to decimal bust that, and once I had that figured out, to multiply both sides by 100 so that I wouldn't have to deal with the decimals. You're free to leave it the other way, it's just easier to solve it from here. And if we're doing by substitution, we're going to solve for x or for y in one of the equations. I think the top one's going to be a lot easier. So solve for x or y. So y is 25,000 minus x. Substitute that back into here. Use parentheses. Distribute. Combine like terms. We're now solving for x. So 3x equals 40,500, x equals 13,500. And then if we plug that back in here, we're going to be able to find y is 11,500. So make sure we specify that in our answer. How much at what percent, how much at what percent, so that it is very clear. Example number 3, substitution, a 3 solution case. Looks kind of complicated, but notice this one's already solved for y, so we could replace this y with this, or in other words, since they're both equal to y, set them equal to each other. So now we're looking at a higher degree polynomial equation. Let's get one side equal to 0. So since the leading coefficient over here being x cubed is positive, let's keep this here. Let's move everything to the left. Set the right side to be 0. So add an x squared, subtract a 3x, add a 1. Now let's try factoring. Remember, back in chapter 2, factoring is not going to work necessarily. Then we have the rational root theorem, where we kind of used a graphing calculator to take a look at some possible zeros, synthetically divide in. But I think this has factors. We could factor out an x as a greatest common factor, and then factor the trinomial. So we get x is 0, x is -1, x is 2, and then choose one of these once you've got your x to plug in and find the y. So I think I might choose the one that's not cubic, so just the one that's squared. So careful on this first one here. Square the x, which would be 1, take the opposite, so -1. 3 times -1, -3, and another -1 is -5. 0 should be easy. Gone, gone, -1. And what about our 2? 2 squared is 4. Opposite of that, -4 plus 6 minus 1. And we get 1, 3 points of intersection, 3 solutions to the system. All right, checkpoint, solve by substitution. Pause here until you've got your solutions. All right, there's definitely different ways to go, but I chose to solve the second one for x. It did create a fraction. I'll get back into here, so 19 minus 3y over 2 times another y, which does distribute. Minus a 3 equals 0. Multiplied both sides by 2 to clear out the fractions, and then moved everything to this side because I did not want the negative y squared. So we get positive 3y squared minus 19y plus 6 equals 0. That factors. We get y is 1/3, y is 6. If it's 1/3, -3 times a third is -1. 19 minus 1 is 18, divided by 2 is 9. And for the 6, 19 minus 18 is 1. 1 divided by 2 is 1/2. And we've got our solutions. Example number 5, solving the system of equations graphically. So we could look in terms of graphing calculator on this, kind of like we did just a moment ago. We'd have to solve for y. So if we're going to solve for y, we get y squared is equal to 10 minus x squared. Square root that. Y is equal to the square root of 10 minus x squared. But don't forget the plus or minus. When we square root both sides, we get positive or negative. Now, you're not going to be able to type that into a calculator. So that's going to be essentially your y1 and your y2 typing into the calculator. So y1 is going to be y1 equals positive square root 10 minus x squared. And y2 is negative square root 10 minus x squared. And this one's not bad. We'll just subtract 2x squared both sides. So there's our y1. If you were to graph that, you get a semicircle. It may look not quite circular on your rectangular screen, but it is a semicircle. y2 is the negative. As we said, that's the bottom part of the circle, so the bottom semicircle. And that connects to make the circle. And there's our y3, negative 2x squared minus 1, which we know is a parabola. Now, as far as go ahead and finding the solutions, again, if we go through and calculate intersection, it's going to ask you, is this your first curve? And you want to say no on that, because remember, that's the semicircle. That's not where our intersections are happening, the top part here. So if you just arrow down to, and it'll then appear here, is that your first curve? You would select yes. And then it's going to say, is this your second curve? And you would say yes. And then it's going to ask you to guess, and once again, just arrow over till you get close to one of these, and then repeat the process to get the other, and we get these as our solutions. Now watch out, because as you get the coordinates, it might say something like -1, negative 3.0000000001, or something like that, and we need to be able to be smarter than the calculator and interpret that and say, it's just having a round issue in the way that it's doing its calculations, and it just really means -3. Example number 6, Ivan the investor bought a popcorn machine for $629. It costs $18 per hour to operate. He charges $45 per hour to rent it out to fundraising groups, carnivals, so on. Write the cost and revenue functions for X hours being rented. Let's start with the cost, which is what it's costing Ivan. So we've got two parts to this cost. We've got a fixed cost, what he bought it for, and then it's operational or his variable cost. So as a function, and let's see if we can practice writing this with function notation. C of x is equal to the variable part plus the fixed part. So $18 per hour, if we say x is the number of hours being rented. And then revenue, see, pause it here, see if you can figure out what the revenue function is. The revenue function is often more simple than most people think. Here's the revenue he's producing, $45 per hour. So it's just 45 times x. All right, so when does Ivan begin to return a profit? Rental hours, keeping in mind that he only rents it out for whole numbers of hours. So you can't say, hey, I want to rent it out for 0.8243 hours. That doesn't really make sense. So he rents it out in hour blocks. When does he turn a profit? Well, when does he break even? He breaks even when the two functions are equal, when the cost equals the revenue. So let's set the functions equal to each other and see if we can solve. So if we subtract 18x on both sides and then divide by 27, you're going to get 23 point something, and it's not a round off problem, because at 23 hours, if you look at cost and revenue, he hasn't turned a profit. He still has more cost than revenue. But once we hit the 24 hours rented, that's when revenue is larger. So this is essentially a round up issue, not a round off problem. 24th hour. All right, 7.2, two variable linear systems. Really what we've been working on anyways, but now another option besides the substitution method is the elimination method, which is choose to eliminate one of your variables. So we want to get coefficients for x or y to be the same number but just opposite signs, like a 5x and a negative 5x, or a negative 2y and a positive 2y. Once we do that, we can add the equations, which will eliminate one of our variables. We'll then solve what's left, and again then back substitute, and we can check. Some places we'll call this the addition method because of step 2, and you'll also see it a little more fancy term, linear combination method. right, example number 2, little chemistry problem. 12 liters of a 6% saline solution is obtained by mixing a 4% solution with a 9% solution. How much of each was used to make the mixture? Again, there's our question, how much of each? So there's where we got to start thinking variables. Define our variables. X could be the amount of this one, the 4%. Y could be the amount of this one. Okay. Specify quantities, be specific. All right, so we do have a solution. So the amount of X and the amount of Y makes 12 liters. And then we essentially have how much saline, which is salt. How much is the actual quantity of salt? Well, for our first ingredient, it's 4% of the X. And for the second ingredient, it's 9% of the Y. And then for the mix, it's 6% of the 12. So if we clean this up a little bit, multiply everything by 100, we get that. Now I'm thinking, well, we don't quite have the opposite, but we can create that pretty easily with multiplication. Coefficients of 1 are really nice, 1 or negative 1. So if I wanted to eliminate the x's, I would want this one to turn into this, but opposite in sign. So I would want to multiply this by negative 4, do it everywhere. Multiply everything by negative 4, and now our x's match up, but they're opposite in sign. Add straight down, x's cancel, 5y equals 24. Divide both sides by 5. So we get 4.8 liters of the 9%. And then we can plug that back in to see how much that is for X. So ultimately we have 7.2 liters of 4% solution and the 4.8 liters of the 9% solution. Make sure we label. Example number 3. Oof. Not really liking that. I'm definitely not liking the fractions. I think we should fraction bust this right away as kind of a first step, and then we'll get into the true solving. So, noticing up top a common denominator of 10. Let's say we multiply everything by 10. And then in our second equation with the least common denominator of 15, multiply everything by 15. And in this case, we get 0 equals 0. Kind of when we did the elimination, everything wiped out. So we need this, not blank equals 0. 0 equals 0, which is the evidence to say, well, when does 0 equal 0? Always. So in this case, we have a special case for our system. We get infinitely many solutions to this, as there are many, infinitely many solutions that work into both. Because what it's saying is that one of these equations is just a multiple of the other. Example number 8. An airplane flying into a headwind travels 1,650 mile flying distance between two cities in 3 hours and 18 minutes. Return flight, same distance. We get back in 3 hours. Find the airspeed of the plane and the speed of the wind. mean, we looked at a more complicated problem like this, not as a system, but with the wind and everything, back in chapter 6 in vectors. But because we're straight into the wind and straight behind, and it's not at an angle, we don't have to worry about the vectors. So what is it we're trying to find? Airspeed of the plane, speed of the wind, those should be our variables. So A would be the plane's airspeed, W the wind speed. So into the wind, we've got a distance problem. Distance equals rate times time. So that's how we're going to base our equation. Distance is equal to rate times time. Well, we know our time, but 13 hours and 18 minutes, we'll probably need to convert that into a decimal or a fraction, something like that. So we're talking about 18 minutes out of 60. And then the rate, that's what we're going to have to figure out, because without a wind, the speed is A. And in this case, we're flying into the wind, so the wind is slowing us down by W. So since it's slowing us down, our rate is going to be A minus W. Now with the wind, same distance. This time the wind is pushing us from behind, making us go faster. So it's A plus W times 3. So there's our system. So originally we're flying into the wind. So we got R1 minus R2, A minus W. Coming back, the wind's pushing us, making us go faster. R1 plus R2, A plus W. All right, so if we divide both sides by 3.3, we get A minus W equals 500. Dividing both sides by 3, A plus W equals 550. Hey, if we just add the equations, the W's will cancel. They'll be eliminated. So 2 times A equals 1,050. Divide by A, 525. Our units, go back for a second. We were talking about miles, so miles per hour. And then plug that back into one of these to find the wind speed, which I think is going to be 25. So the plane is at 525 miles per hour. The wind is at 25 miles per hour. Please, please make sure that your answer makes sense. If your wind is 300 miles per hour, I believe that might be larger than the wind has ever been recorded on this planet. So make sure that it's reasonable. If your plane is flying at 13 miles per hour, it is not going fast enough to escape gravity. That cannot happen. So make sure it's reasonable. That's it for today. I'll see you next time.